Hi everyone, this is me, Sonia, trying to explain this geometry problem. It was suggested by me for last year's Manchester Maths League 2023-2024. So it goes a bit like this. So there's a triangle ABC, the angle B is 60 degrees, C is 40 degrees. You have this relation, so CD, where D is a point on the line BC, such that C is between B and D. Such that this happens. So CD is the sum of all the sides, the length of all the sides of the triangle. So AB plus BC plus AC. And they are asking to find the angle ADB. So basically this angle. I mean, you can predict it's really small. This is not up to scale. As I said, it's a really small angle. D would be much further, like somewhere here. But it's good enough. So what this problem wants us to do is to basically put all of these sides on the line BC. So basically, you want to make a construction such that you will have something either of length AB or AC on this line, CD. So basically, I'm just gonna do it, and I hope you'll later on basically understand the construction. So basically, the first step is we take this point E on CD such that CE equals to AC. So I'm just gonna mark it like this. So in fact, it is gonna be an isosceles triangle. I tried. Again, without saying, it goes without saying, when you have these geometry problems and you have angle measurements, you literally find out all the angles that you can. So 60, 40, so automatically this one is 80. This exterior angle is 140. This is isosceles, so it's going to be 20, 20, just by looking at ACE. Sorry, I shouldn't. One sec. I didn't mean to do that. Right. We have this triangle. So that's really cool. Okay, so we have CD, in other words, is CE plus BE AC. That's really cool. So that literally tells us CD is CE plus ED, which by our construction is AC plus ED, which by the thing we're given, it's AB plus BC plus AC. So basically we're left with ED by cancelling terms is equal to AB plus BC. So this one here. Cool. Now I'm gonna do another construction. Trying to, let's say, bring BC into this, because BC, again, it's a bit inconvenient because it's beyond on the other side of C, let's say. So I'm gonna do it like this. I'm gonna put a G on this AE such that AB equals to AG. So I'm gonna try to make it a bit plausible. Sorry, my bad. It's G. I apologize. I'm just gonna. Sorry. G. And I'm gonna write this together. So by construction, I'm gonna write them like this. AB is equal to AG. Okay, from here we have a lot of angle measurements again that we can make. This is isosceles, this is 100, so this one's individually are 40 and 40. This one's 20, this one here below it, because it's the difference from 60. So now we have a great result. If you're have a more or less trained eye. Okay, I'm back. So we were here. We made the construction with G, and I want you to focus now on this quadrilateral ABCG. And I'm gonna go to another page for now to illustrate the point. Well, cyclic quadrilaterals, they're a very cool tool in competitive like geometry problems, like from, I don't want it to look like a square. I don't want it, okay, it's not a square. It quite literally is a quadrilateral, a four-sided thing that you can inscribe in a circle. And because of circle properties, again, if you note the center for it, again, it's not a scale, it's not a good circle, but I just wanted to get the idea of it. So these radiuses from the center to all the vertices will be equal. Another property is that the opposite angles are adding up to 180. They're complementary, I think it's called. But the property which interests us is the fact that these angles, which are the ones defined by the diagonals with the opposite sides, and I'm gonna, I don't know, red, this one with this one, I don't know, pink, this one with this one, and purple, let's say, and this one and this one are equal. The whole reason is that they are opposite the same arcs. So if you remember, for example, look at this purple one, it's opposite this arc from this point to this one. So it's the measurement of the angle is the length of the arc divided by 2. And the same with this purple one here. It's just this arc divided by 2. This is to keep in mind. And this is literally what we're identifying here. Again, some trained eyes might have, this is a bit natural. It becomes natural for you to see these things. So yeah, indeed, A, B, C, G will be cyclic because these angles are equal. And you can straight away, and these two, you can make the conclusion straight away. It's cyclic because those angles are equal. So it's a cyclic. So what that means is we're going to do all the rest. So what that means, this one's also 80 because it's equal to this one. This one's also 40 because it's equal to this one here. So that's great. So again, I'm going to change colors for a bit. This whole thing will be 80, which is 80 here. So that's great. That means we have another isosceles triangle here. I'm going to write it with like a curly thing. So we have BCG is isosceles with the base CG. That's great. Another thing that we can quickly observe, 2020. Cool. Another isosceles, BGE, curly thing here. Hot. That's amazing. So basically what the information that we get is BC, which is the initial red curly thing, equal to yeah, GE. Okay, I think that's fine. Okay, so one more point I was trying to make is by summing things up. This is what we found before. And now we know that AE is this two-line thing plus the curly thing, which is indeed AG plus GE, which is by all the things that we said before. By isosceles triangles, AG is equal to AB by the construction that we made. GE from the above is equal to BC. Cool, amazing. From both of these, we get indeed ED is equal to AE. This is it, like this is it. So AD is isosceles, so with the base AD, again, just imagine it. This whole exterior angle is 160. So indeed, these two small will be 10. So this is the angle that we wanted. ADB is equal to ADE, which is 10 degrees. Yeah, that's it. That's the solution. Thanks, guys.